Okay, let's wrap up our C amplifier analysis. So we stopped, actually not quite here, that's a different section. Stopped here. Okay. All right, so we have a C amplifier using a BJT. We are given the characteristic curves, the input side and the output side. And we saw how to plot the load lines. The load line procedure does not change. It's exactly the same as what we did for the diodes. It's the same as what we did for the Zener diode. Okay. So we applied KVL on the input side. We applied KVL on the output side. We generated our equations, plugged in X and Y is equal to 0, and determined the values for the coordinates. So for a BJT, we have two sets, right? We have the input side, we have the output side. So on the input side, we have VB and IB. On the output side, we have IC and VCE. So we're going to see how we can obtain output voltages from the input load line. Okay. What we're going to do is we're going to find the three intersection points that correspond to our output. Okay. So this is an explanation of the method before we proceed to the actual example. Right. This is not the actual example itself. So let's say we have plotted our load line right here on the input. We have an intersection point, so we have a Q point, right? Now we apply an AC input on top of our DC biasing voltages. So this Q point is a result of our DC biasing voltages, which is VCC and VBB. So VBB and VCC give us this load line on the input side. So we have one intersection point, which is right here. Now, if you apply an AC input on top of our DC voltages, then that Q point is going to shift. It's going to move up or down, depending on the AC input, right? And so that's what happens here. So let's say IB changes from some random numbers, and I chose 10 microamps to 30 microamps. So let's say it changes from 10 to 30 microamps. So on the input load line, we'd have three different points. We'd have three different load lines. Those three different load lines will intersect or characteristic in three different points. The X coordinates of those points, sorry, the Y coordinates of those points would give us the values of IB. Okay. On the output side, now this is the output side. The output side is a function of, sorry, output side is a plot of IC as a function of VCE. But there are multiple data points. There are multiple data sets. Each data set of IC versus VCE is a result of an applied input voltage of IB, or applied input current of IB. So this line is a plot of IB equals 10 microamps. This line is for IB equals 20. This is for 30. This is for 40. This is for 50. So output side is a set of data points. Okay. Once we find IB values, we find the corresponding intersection point of the output load line for those three values. Meaning we are interested in 10 to 30. And in this case, it's 10, 20, and 30. Okay. And what we will see is that the output will move in response to the input. Okay. We have a load line on the output, and we can see the change in the output as a response to the input. So far, so good. Let's go into the example, and then it will start making more sense. So we are given, for the same circuit, we are given values for VCC and VBB. We are given the resistor voltages, RC and RB, 40 kilo ohms and 2 kilo ohms. We are given V in of T as 0.4 sine of 2000 pi T. V of T is V peak sine omega T. VP means one peak, means your input voltage swinging between plus 0.4 and minus 0.4. Again, V in of T is Vp sine omega T. So the peak value of V in is plus 0.4, but it also notes the negative peak, which is minus 0.4. So your V in is switching from minus 0.4 to plus 0.4. Now let's plot the load lines for the input side. We apply KVL to the input side. We find values for IB and for VBE. Okay. IB is VBB plus V in over RB. And VBE is simply VBB plus V in. If V in is equal to 0, it's the same as that what we did for the diode. Okay, when V in is 0, when you're not applying any AC input, it's simply what we did for the diode. But now, because V in is changing, we incorporate that into our equations. And so there are three values for V in. V in equals 0, which is right here. And max value of V in, which is plus 0.4. And the minimum value of V in, which is minus 0.4. And so you can see I obtain IB values of 30, 40, and 50 microamps. So I have the Y coordinates for the input base current. Oh, not that, sorry, this 30, 40, and 50. Again, we are plotting the line, so we need the two endpoints of that line. And because we are applying an AC input voltage, there are 3 points. One is when V in is 0, one is when V in goes to its positive peak, the other one is when it goes to its negative peak. So 3 points. V in is at 0. That's the Q point that is a result of the VCC and VBB DC voltages. And then when V in goes positive, the entire line shifts up. When it goes negative, the line shifts down. We obtain VBE values as 1.2, 1.6, and 2 volts. Those are the points that are indicated right here. So you now have the x-axis values. And once you have those values, join them together to obtain your load lines. Let's take a pause. Let me know if you have any questions. So far, so good. Again, so far, the only difference from the diode load line analysis is the addition of V in. Other than that, it's exactly the same steps. Okay, we are given the characteristic curve for the input junction, which of course, because it's forward bias junction, it looks like a diode. We want to plot a load line, so we plotted a load line. But now V in, instead of just being 0, also goes to plus 0.4 and minus 0.4. So now we have 2 additional load lines for a total of 3. Okay, so our input is changing like this. Okay. So now that the characteristic plot that's shown here in blue is intersected by those 3 load lines. If you extend those to the left, you get the values for the base current for those 3 points. Y-axis is IB. So the coordinates, the Y-axis coordinates for those intersection points, these 3 intersection points, they give us the values for IB. And they turn out to be 15, 25, and 35. Okay. That is observation from the graph. We did not calculate those. Again, it's the Y-axis coordinates of those 3 intersection points. That would be the operating point of the diode or the input side, basically. We don't need VBE for anything, so we are not determining those values. But if you wanted to, you would simply extend these values right here on the x-axis. Because it's a forward bias diode, the difference between VBE would be very, very small. Would not move much. We good so far? Any questions? Shall we go to the output side? Okay, moving on to the output side. What do we have here? On the output side, we have IC as a function of VCE. IC changes in response to IB, right? If V in is V in is 0, IB is fixed at a point. So then IC and VCE will also be fixed. But we need to plot the load line at the output side also. The lines in blue are the characteristic curves, right? Each is a data set for a function of IB. IB is 0 microamps, no input. There's a function of IC, plot of IC as a function of VCE. 10, 20, 30, 40, 50, and you have a set of curves right here. Okay. Then you apply specific VCC and VBB voltages to bias or Q points in the center. So on the output side, we'll go here and I'll show you what we did here was we applied KVL on the output side. Right? We applied KVL on the output side to plot the load line. And these are the 2 points. VCE is equal to VCC and IC is equal to VCC over RC. So in the case of our example, in order to plot the load line, VCE is equal to VCC, which is equal to 10 volts. And then IC value is VCC over RC, which is equal to, what is it, 2 over 1000, so 5 milliamps. And those 2 points are right here. So again, load line process does not change. This time we are plotting the load line for the output. And so on the output side, apply KVL, obtain our equations, plug in X is equal to 0 and find the value for Y. Plug in Y is equal to 0, find the value for X. Once you have those 2 points, join them together, you have your load line. Now the output load line intersects all of those plots. Specifically, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 plots or 10 sets of data. Right? So load line intersects the output characteristics in 10 different points. So you have 10 different intersection points. Which ones do we need? So we go to the input side, we find the values for IB, and we bring those 3 values here. Those 3 values were 15, 25, and 35. And so those 3 lines are the plots that we are interested in. Again, output load line intersects in 10 different places, 10 different points. We need only 3, 15, 25, and 35, which we obtain from load line analysis of the input side. So the plot at 25 is the one when V in is equal to 0. Plot at 15 is when IB is minimum, or when V in goes to minus 0.4 volts. And then this at 35 is when V in goes to plus 0.4 volts, positive half cycle. And these 3 intersection points give us our solution for the output. If you extend it to the left, the Y coordinates give us the value for IC, the collector current. The X coordinates give us the value for VCE. And there's a bit more, more analysis, not explanation of the analysis. But let's take a pause here. Let me know if you have any questions. Do the steps make sense? Okay, the process of the load line is the same on both sides. But on the input side, you have 3 different load lines. On the output, you just have 1, but 3 different intersection points that we need to find, and we obtain those from the input side. Okay. All right, so how do we interpret this? Let's look at our V in. This is V in. This is V in of T. Only goes from minus 0.4 to plus 0.4. Obviously, this is not to scale. This is in microamps. This is in milliamps, and this is in volts. Okay. So V in goes from plus 0.4 to minus 0.4. Intersection point on the IB is 25 microamps here, and IC is approximately 2.5 milliamps. When IB goes minimum, which is 15 microamps, right here, 15 microamps, my corresponding IC is 1.5 milliamps, approximately a gain of 100, which makes sense. If beta is 100, gain should be 100, right? IC should be 100 times IB. So 15 microamps and 1.5 milliamps. And then when IB goes maximum 35 microamps, you get IC value of 3.5 milliamps. So far, so good. IC is an amplified version or amplified form of IB. And IB is a result of the input voltage that is being applied, V in. But now if you look at the x-axis coordinates, the x-axis coordinates of these intersection points, what do you see? The maximum value of V in results in the minimum value of VCE, which is 3 volts. Q point is right here, gives us 5 volts. And the minimum value of V in, the minimum value of IB, gives us the maximum value for VCE. So the output voltage is flipped with regards to or with reference to the input voltage. It's amplified, it's going from 3 to 7 volts. It's from 3 to 7 volts, but it is 180 degrees out of phase. Minimum value for V in gives us the maximum value of the output. Okay, so it is 180 degrees out of phase. Amplified and inverted. Does everyone see that? So a small change in input, 0.4 to minus 0.4, gives us an amplified output that has a value of 3 volts to 7 volts. What it is doing is you have VCC, 10 volts applied VCC, and then applied V in, right? V in has some sinusoidal shape. So what the transistor is doing is it is taking the VCC and giving it the shape of your AC input signal. Not the most technically accurate, but the analogy works. And energy doesn't come from thin air. It comes from the VCC voltage that is being applied. So your DC voltage is now given the shape of your AC input signal. And as a result, you have an inverted output. Also, the AC output is at 5 volts. So if I was to plot this, this was time and this was voltage V, the actual waveform wouldn't be at ground. Voltage waveform would be here, actually. At 5 volts, not at 0 volts. This would be here, 3 volts, be here, 7 volts. So my output waveform is also clamped. It has a DC component. So it's clamped at 5 volts. Does that make sense? All right, questions? Okay. Input V in, output VCE. Amplified and inverted or out of phase. This variation is only 0.8 volts, whereas this variation is 4 volts. Okay, so output is an amplified version of the input voltage. There's two more things we need to talk about here. Well, actually, it's one thing, which is distortion and clipping, but it can occur due to two different reasons. Okay, but does anyone have any questions before I move on? Okay. So distortion can occur due to the clipping of the waveform. Okay. And this image shows a result of a large input voltage being applied. Instead of 0.4 volts, let's say input was already 2 volts or 3 volts, and the amplification gain remains the same. The output obviously cannot exceed the limits that are imposed by VCC. If VCC is 10 volts, output cannot be more than 10 volts. Energy does not come from thin air, right? And so if you're applying a small output, if you're applying a small input, your output would be within your design limits. However, if the input is now large, probably not quite as large. Larger input will result in clipping and distortion. Okay, clipping and distortion. So that's one. If you have a gain of 10, you apply like 1 millivolt, you'd get 10 millivolts at the output. If you have a gain of 100, you apply 1 millivolt, you get 100 millivolts at the output. If you apply 5 volts at the input for a gain of 100, we are not going to obtain 500 volts. We will only obtain what the max VCC is, minus a few voltage drops. The rest will be clipped off because the output saturates at that level, flat lines. That's a result of a very large input. The second occurs due to a poorly designed biasing circuit. And that means, going back to the circuit diagram right here, this is chosen by designers. The value for RB, RC, VCC, and VBB are chosen by the circuit designers. The values of these components and these voltages will bias the circuit and fix the operating point in the middle of the active region. But let's say the circuit is not well designed. What will happen then? That will shift the Q point either up or down the load line, the actual Q point, without any AC input. And if that happens, let's say the Q point shifts up right here. Now, if you apply your input, your output would be somewhere here, closer to saturation. So your output might go like this, but it hits saturation. And one end of your waveform is chopped off. So obviously there's nothing to the left of it. Make sense? At least the illustration makes sense. If it's one end of the graph, one positive or one negative cycle will get clipped off. The same thing happens if the circuit is designed poorly and the Q point is closer to cutoff. If your Q point is somewhere over here and you apply an input like this, amplifier gain doesn't change, but now your positive cycle gets clipped off. In both cases, the result is distortion, which is what you would notice in an audio system. You would notice this as tearing sounds coming from a speaker. You have an audio system, you turn the volume up too high, now you're forcing too much voltage and current to go through the system, and perhaps your speaker also cannot handle it, and so that's how it sounds. It sounds as tearing noises coming from your speakers. So that's a distortion and clipping that occurs due to a large input signal or due to a poorly designed biasing circuit. All right, questions? This is going to be on the Monday quiz. Friday quiz is BJT fundamentals, and then Monday quiz would be on CE amplifier. Okay. One drawback of this kind of circuit is that it is highly dependent on the beta of the transistor. Okay. So if a transistor is rated for 100 current gain, and you take it out, you plug a different transistor in there, perhaps the exact same model, perhaps even manufactured at the same time on the same substrate, but the beta could be highly different. Instead of 100, it would be 150, it would be 200. Okay, and it does happen in real life. So if that happens, then the circuit is not going to function as it's supposed to. So there are many other biasing circuits that are designed in a way that the circuit operates independent of the transistor beta values. One of those, and one of the most popular ones, is known as a 4-resistor bias circuit. And obviously the 4-resistor comes fact that you have R1 and R2, two resistors connected to the base, one collector resistor, and one emitter resistor. Okay, so 4 different resistors, hence a 4-resistor bias. On the input side, R1 and R2 form a voltage divider network. It forms a voltage divider network as seen from the perspective of the base, from here. Hence, this is also known as a voltage divider bias. Okay, voltage divider bias. And if you noticed, if you compare this to the previous circuit had 2 different power supplies. You had VBB and you had VCC. Right? But there's only one single power supply here. That is VCC. We don't need to change, or we don't need to apply 2 different voltage sources. Right? We don't need to apply 2 different separate voltage sources. So we need to go from the left to the right. And for that, we'll call upon Thevenin to help us out. We need to find the Thevenin equivalent network as seen by the base emitter junction. Okay, as I said, we need to go from the circuit on the left to the circuit on the right. You need to combine it one single resistor and one single voltage source, as seen by the base emitter junction, meaning how does R1, R2, and VCC look when it's viewed from the base. And to do that, we divide it up and observe circuit from the base emitter junction. The circuit itself has not changed. It is just redrawn in a different manner. Okay, the circuit itself has not changed. So VCC applied at the top, VCC applied at the top, at the right, and on the left side. You're simply breaking it up. So now we need to convert this to this, where VB would be the Thevenin voltage and RB would be the Thevenin resistance. This is the base emitter junction. Okay, base emitter junction. VTH can be found by applying voltage division principle. And RB can be found by replacing VCC with a short circuit and measuring REQ between the base emitter junction. This is R1 and R2. And because we are temporarily replacing VCC with a short circuit, it puts R1 in parallel with R2. So when we measure REQ between the base and the emitter, we see R1 parallel R2. Okay, R1 parallel R2. Okay. All right. Let's pick up the pace a little bit. We can model the collector as a dependent current source with a value of beta times IB. IC is a dependent current source dependent on the value of IB, the base current. IC is beta times IB. So we can redraw the circuit to look like this. We apply KVL on the input side, and we apply KVL on the output side. Okay, 2 KVLs. We obtain this equation for the input. The input side, we can plug in IE is beta plus 1 times IB. IE is the sum of IB and IC, right? So it's IB plus IC. IC is beta times IB. So it's IB plus beta times IB. You rearrange the terms. This is what you obtain. Beta IB plus IB. So if you plug that in to this emitter resistor voltage, you obtain this expression, and we want to rearrange the terms to find an expression for the input current IB. Okay, we want to find the input current IB. In the load line analysis, we found the values for IB by plotting the load lines. If you perform a mathematical analysis, we need to find an equation that describes IB. So, apply KVL, rearrange the terms, and we obtain an expression for IB. And you can notice beta is there as part of that equation. On the output side, it's the same expression. VCE is equal to VCC minus ICRC, and then additional voltage drop for the emitter resistor, RE. So if we had an example, we'd bias the circuit. We would calculate IB, from RB and VB values, and then we can calculate the output voltage. We can plug in IC and IE once we know what our input voltage is. Okay. So let's look at an example with some values. We have that same circuit. Now we have the resistor values. And VCC is plus 15 volts. So you're asking to find the output if beta is 100 and beta is 300. Output simply means find the collector current and the collector emitter voltage, VCE. First step, find RB, find VB. Standard equations, we already derived those. So we can find RB, we can find VB. Plug in the values into the equation for IB. If beta is 100, we obtain IB as 41.2 microamps. If beta is 300, we obtain IB value as 14.1 microamp. Note the difference. The higher the beta, the lower the input current. For 100, it's 41.2. 300 is 14.1. And this results in an IC value of 4.12 milliamps and 4.24 milliamps. Again, the purpose of this 4-resistor bias circuit is to make it independent of the transistor beta value. Okay, so we can see when we plug in values of beta for IB, we obtain 41.2 and 14.1. So the higher the beta, the lower the IB. So when we go to find IC, which is a product of beta times IB, it balances out. And IC does not change much from transistor to transistor. So the IC value is 4.12 and 4.24. A change of 200 in your current gain did not result in a vast difference, or not even more than 10 microamps. Well, actually, it's more than 10 microamps. It's 0.12 milliamps, about 120 microamps. But still, it's an extreme example, right? A change of 200, beta 100, beta 300. It's not much difference in your output current. If you find the output voltage, plug it into the output voltage equation, VCE, and you obtain VCE values as 6.72 and 6.51 volts. Again, there's not much difference between the two voltages. Typical beta values, let's say if you have a transistor of 100 beta and you plug in another transistor, same model, you might have a variation, might have 110, 120, maybe 150. But you're not going to have something like as far apart as 100 and 300. So if you plug in a beta of even 150 in here, the difference would be even smaller than what is shown here with these calculations. Okay. So the point being, beta variation does not affect the output. Not much anyway. All right. Any questions? So in the interest of picking up the pace, I had my annotations on there. These are already available to you at your end in the class notebook. It's also available on the recorded video. Please review those, review the slides, review the annotations and the equations and the calculations, review the steps. If you run into any issues or problems or need any clarification, please reach out to me. I'm available in my office later this afternoon. I'm also available over the weekend via email And if need be, I'm also available to meet on Zoom. So if you have any questions, just send me an email. If I cannot answer or clarify the doubts via email, then we'll meet on Zoom. Okay. And so that's the end of chapter 2. On Monday, we'll begin chapter 3, which is op amps. All right. All right, we still have a few more minutes, so I'm around if you have any questions. If you don't have any questions, then I'll be in my office. Also, finally brought the wafers for show and tell. So these are actual silicon wafers from a production facility. And so I wouldn't do that. These are brittle. If I drop them from even like an inch or 2 inches high, they're like, they could shatter and break. But I'll pass these around so you can take a look. Those are from some production facility. A former student gave them to me. And these are actual silicon wafers fabricated by actual Cal Poly students in our very own clean room. So this is what you get to do if you take the clean room class. And I neglected to mention this last class. Most of you are mechanical engineers. You know who the director of the clean room is? Hans Meyer. Some of you do know it. So Dr. Hans Meyer of mechanical engineering, he is the director of the clean room. Dr. Benjamin Hawkins from the BMed department, he is the associate or the assistant director of the clean room. And Hans, Ben, and I, Hans and Ben have been doing it for a long time, and I've been doing it at a different university where I used to teach clean room lab classes. So whenever it fits my schedule according to the department, Hans, Ben, and I each teach one lab section of that clean room class. It's only offered once a year in the winter quarter. Dr. Hawkins teaches the lecture class, and then all three of us teach one lab section each. And so those wafers in the small square container, those are the ones that are actually built in the lab by the students. So if it's something that interests you, keep a lookout for this next winter when you're registering for classes. All right, have a good weekend, and I will see you all on Monday. If you have any doubts, I will see you before then.